Good morning, everyone. I'm Rahul Chowdhury, and welcome to our comprehensive course on solid design principles. Today, we're going to explore one of the most fundamental concepts in software engineering that will transform how you approach code design and architecture. SOLID is an acronym, and each of these 5 letters represents a core design principle that every professional developer should master. These aren't just theoretical concepts, but practical guidelines I've used throughout my 15 years in the industry to build maintainable, robust software systems. These 5 principles work together to help us create software that is maintainable, meaning it's easy to fix and update, reusable, so we can leverage existing code in new contexts, modular with clean separation of concerns, and extensible, allowing us to add new features without breaking existing functionality. These principles were originally introduced by Robert Martin, also known as Uncle Bob, who is a legendary figure in software development. What makes SOLID so powerful is that it provides a systematic approach to writing clean, professional code that stands the test of time. Over the next several sessions, we'll dive deep into each principle, see real-world examples, and practice applying them through hands-on refactoring exercises. By the end of this course, you'll have the tools to evaluate and improve any code base using these foundational guidelines. Let's begin our journey into better software design. Building on our introduction to SOLID principles, let's dive deep into the first and arguably most fundamental principle. The Single Responsibility Principle, or SRP, is the foundation that all other SOLID principles build upon. It's elegantly simple in concept, but profound in its impact on code quality. At its core, SRP states that no code unit should have more than one well-defined responsibility. Think of it as the do one thing well philosophy applied to software design. This principle applies universally across your codebase, whether you're writing functions, designing classes, or organizing packages. Each should have a single, clear purpose. When we violate SRP, we create a cascade of problems. Code becomes difficult to test because we're testing multiple concerns at once, hard to maintain because changes affect multiple functionalities, and complex to understand because developers must grasp multiple concepts simultaneously. Here's a classic violation example. Imagine a class that handles both user authentication and email sending. This violates SRP because it has 2 distinct reasons to change authentication logic updates and email service modifications. These are completely separate concerns that should be handled by different classes. Remember, SRP isn't about having the smallest possible classes or functions. It's about ensuring each unit of code has one clear reason to exist and one reason to change. This creates a solid foundation for all the SOLID principles we'll explore next. Building on our understanding of the Single Responsibility Principle, let's now explore the second SOLID principle, the Open/Closed Principle, or OCP. This principle is fundamental to creating flexible and maintainable software systems. The Open/Closed Principle states that software entities, whether classes, modules, or functions, should be open for extension but closed for modification. This means we should be able to add new functionality without changing existing working code. Now, how do we achieve this seemingly contradictory requirement? There are 3 key implementation strategies that make this principle work effectively in practice. First, we use abstraction and interfaces. By programming to interfaces rather than concrete implementations, we create extension points where new behavior can be plugged in without touching existing code. Second, inheritance and polymorphism allow us to extend base classes with new functionality. Subclasses can override or extend parent behavior while the existing code continues to work with the base abstraction. The ultimate benefit of following OCP is risk reduction. When we add new features by extending rather than modifying, we eliminate the risk of breaking existing functionality that's already been tested and deployed. This leads to more stable and reliable software systems. Building on our understanding of SRP and OCP, let's now explore the third SOLID principle that ensures proper inheritance relationships in our code. The Liskov substitution principle, or LSP, is named after Barbara Liskov, who introduced this concept in 1987. This principle is fundamental to creating robust, object-oriented designs. The core idea is beautifully simple yet powerful. Objects of a superclass should be replaceable with objects of its subclasses without breaking the application's functionality. In other words, if your code works with a base class, it should work seamlessly with any of its derived classes. To achieve this substitutability, there are key requirements that every subclass must fulfill. Most importantly, subclasses must maintain the behavioral contract of the parent class. This means they can't weaken preconditions, strengthen postconditions, or throw unexpected exceptions. Think of it as a promise. If the parent class promises certain behavior, the child class must honor that same promise. A classic example is the rectangle-square relationship. While mathematically a square is a rectangle, in programming, a square subclass might violate LSP if it doesn't behave consistently with rectangle expectations. For instance, if setting width and height independently breaks the square's equal sides constraint. When LSP is violated, you'll encounter unexpected runtime errors and behaviors that are difficult to debug. This principle ensures that inheritance truly represents and is a relationship that works in practice, not just in theory. Now let's move on to the fourth solid principle, the interface segregation principle, or ISP. The interface segregation principle is all about creating focused, purpose-driven interfaces rather than bloated, monolithic ones. The core idea is simple but powerful. Clients should not be forced to depend on interfaces they don't use. Think of it like a TV remote. You don't want a single remote with buttons for every possible device when you only need to control your TV. Instead of creating one large interface with many methods, we create multiple smaller, focused interfaces. This approach reduces coupling between components and increases flexibility in our design. A classic example is splitting a large worker interface into separate interfaces like workable, eatable, and sleepable. This way, a robot worker class doesn't need to implement eating and sleeping methods it will never use. ISP helps us build more maintainable systems where changes to one interface don't ripple through unrelated parts of our codebase. It's about respecting the boundaries between different responsibilities. Now we arrive at the fifth and final solid principle, the dependency inversion principle, or DIP. This principle is particularly powerful because it fundamentally changes how we think about dependencies in our code architecture. The core idea is simple yet profound. Depend on abstractions, not concrete implementations. This means our code should rely on interfaces or abstract classes rather than specific, concrete classes. Let's break down the key principles that make DIP so effective. There are three fundamental concepts we need to understand. First, high-level modules should not depend on low-level modules. Think of high-level modules as your business logic, the important stuff that defines what your application does. These shouldn't be tightly coupled to low-level implementation details. Second, both high-level and low-level modules should depend on abstractions. This creates a middle-layer interfaces or abstract classes that both sides can depend on without depending on each other directly. Third, details should depend on abstractions, not the other way around. Your concrete implementations should conform to the abstraction, rather than forcing the abstraction to match your specific implementation details. When we apply DIP correctly, we achieve loose coupling between our modules, making our code much easier to test through dependency injection, and creating a more flexible architecture that can adapt to changing requirements. This principle ties together beautifully with the interface segregation principle we just covered, creating a robust foundation for maintainable software design. Now that we've explored each solid principle individually, let's bring it all together and see how they work in practice. We've covered a comprehensive journey through all 5 principles, and now it's time to understand their real-world impact. The true power of solid principles emerges when they work together to create robust software architecture. Remember, these aren't isolated rules. They complement each other beautifully. When you apply SRP, your classes become focused. When you follow OCP, they become extensible. LSB ensures your abstractions are reliable, ISB keeps interfaces lean, and DIP creates flexible dependencies. The benefits we've discussed throughout this course become very tangible in practice. You'll find that maintenance becomes significantly easier when each class has a single responsibility. Testing becomes more straightforward when your code follows the open-closed principle. And adding new features becomes less risky when your architecture respects proper substitution and interface segregation. We've also learned about common pitfalls and how to avoid them. Remember to resist the temptation to over-engineer solid principles should simplify your code, not complicate it. Start with simple solutions and refactor as your understanding grows. Watch out for premature abstractions and always consider the context of your specific project. As we conclude this comprehensive exploration of solid principles, your next steps are crucial for mastering these concepts. I encourage you to practice applying these solid principles in your own projects. Start small, perhaps refactor a single class to follow SRP, or identify an area where you could apply the open-closed principle. The more you practice, the more natural these patterns will become. Remember, becoming proficient with solid principles is a journey, not a destination. Thank you for your engagement throughout this course, and I'm confident you'll create more maintainable and robust software using what you've learned today.